The first section of National Electric Code is definitions. And we're going to leave the definitions for later as we get to the words in the code, then we'll bring the definitions up. Code is intended to be a minimum set of safety requirements. You will encounter situations where, you might be in the attic and you might say, okay, well, this attic is a dry location, but because I'm poking so many holes in the roof, should I consider it a damp location or a wet location? Well, code only says dry location. That doesn't mean you can't apply common sense and make your design more robust. Then again, you can't just go willy-nilly substituting products. There might be a difference between a bundled dry cable and a single conductor wet cable in the eyes of code, and we need to figure out what those nuances are in order to kind of perfect our solar design. And code applies to both public and private premises, as well as mobile premises like RVs, parking lots, yards, temporary businesses like a sound stage or something like that. All of these things are governed by electric code as well as the point of interconnection. We define all of our terms, and then we get into installation requirements. And so the beginning sections of code are kind of establishing the ground rules for terms, for supplying power to the building. But before we get to the building, we have to talk about what supplies power to a panel. So we're defining our feeder circuit, then getting into our wiring methods. And then later on in code, we get more complicated. Now that we have feeder circuits defined and wiring methods defined, then we get into the sizing of conductors and cables, then we get into general equipment, and only later in code do we get to the specialty stuff like solar arrays and distributed power. So there is going to be some repeating content in code as we move along, because what is relevant to, say, the utility feeder conductor might also be relevant to an AC branch circuit that is later defined in code. So there is a lot of repetition. And what that means is if we start at the beginning and really understand the reasoning behind all of these terms and conditions, then we will be better able to comprehend and understand code in the later sections. And also you can prepare for your master electrician exam. And when you get questions about motors or other things that your swimming pools, you might think to yourself, well, I don't know about swimming pool design specifically, but now I know about running conduit through concrete. So what about that knowledge is relevant to swimming pools? Things like that. Deteriorate agents. No conductors or equipment shall be located in damp or wet conditions, exposed to gases that have a deteriorating effect or excessive temperatures unless identified for that purpose. So, solar arrays and generators are usually outdoors. And that means they're exposed to the elements. If they're protected, if they're sheltered outdoors, if they're not subject to water spray on a regular basis like rainfall, that's not necessarily a wet location. That could be a damp location. You can have interior wet locations. A wet location is something that gets sprayed with water. So a car wash might be inside of might be enclosed, but that would be an interior wet condition. Usually, a rooftop would also be a wet condition. Now, solar arrays and rooftops undergo extreme temperatures in addition to a wet location. And then in some solar arrays are exposed to gases, so flooded lead acid batteries, and generally any kind of batteries that require watering and regular maintenance will emit gas that has a deteriorating effect on metal. And so in solar power, we have a lot of specialty cabling and equipment And it's not so much that the cable is particularly unique. You know, it's not like a fiber optic cable that has a billion different connectors to it. It's a single conductor cable. And you might go into Home Depot and think, well, there's a billion single conductor cables out here. Yes, but are all of them listed for wet conditions? Are all of them listed for excessive temperatures? And so what's complicated about on-site renewable design is that if you're a general contractor, general electrician, you just may not connect all the dots through on saying, well, what's the difference between a wet location and a dry location? You might get to the store and realize, well, this cable is not listed for outdoor use. So we have to learn how to match all that stuff up. So a damp location would be under a porch, you know, a basement, some warehouses, car washes. A wet location, a concrete slab is considered a wet location. So I think that's, you know, kind of one of the more, I guess that's, you know, you'll experience that a lot. Areas exposed to water saturation, unprotected areas exposed to weather, dry locations, you know, that's like the inside of your house. It can be temporarily damp or wet during construction. That doesn't mean it's a dry location. Now, I can tell you from industry experience, the locations can trip you up and weather ratings can trip you up because solar equipment is so robust and it is designed for outdoor use. So you might be buying inverters that are NEMA 3R or even sometimes NEMA 4 or even NEMA 6. So very robust, waterproof inverters. You may be buying micro inverters or module level electronics that go up on the rooftop, and they have, you know, they're listed for the extremes and they're listed for the weather. Same with solar modules. Your solar panels are designed to go up on the rooftop for a long period of time as well. The danger is during construction, if the array is not complete, fully complete, you know, you might have loose connectors and wirings hanging off all of these components. And I have seen damaged electronics where the install crew might mount the optimizers or microinverters at the end of the day, and then they don't plug them up and it rains overnight. Water gets into the connector. Or inverters stored out on a job site with a tarp over them, and they're a NEMA 4 inverter, but then something goes wrong with the construction of the ground mount array. The material sits outside, it rains a while, humidity gets under the tarp and into the box and starts deteriorating the electronics because they're not fully plugged up yet. So don't confuse, if you're designing something for a wet environment, you know, when it's not installed, that doesn't mean it's still rated for the wet environment. You know, that can be a very costly mistake. So, you know, think about your locations. It makes, you might worry about temperature sizing. You know, do I use a 75C cable or a 90C cable? Well, you know, if you're up on the rooftop, that's a very hot environment. You know, that's what the high temperature cable, the 90C cable, is designed for. So yeah, you should use a higher elevated temperature cable on a rooftop. You know, inside your conduit, inside the attic, where you see this conduit going up to the rooftop. Well, that conduit is not just in the attic, it's going up to the rooftop. And we'll see code requirements that say at that point, you need to put foam sealant into that conduit. Because what can happen is the temperature difference between the attic and the atmosphere can cause condensation and moisture, and water can get into that conduit. Or likewise, the you know, conduit that's buried into the ground, that's a wet location, inside the conduit, it's going to leak. It's going to get humidity into it, and that's considered a wet location too. So, you don't need to worry so much about your material selection and what wire type you're using if you start with the premise of, okay, is my environment wet, damp, or dry? Is it going to experience high temperatures, or is it air conditioned and inside? Are there any batteries in the room, so I have to worry about a corrosive environment? Or am I right on the coastline, or am I on a chicken farm? What's a corrosive environment versus if there's no gas in the area? And from that point, that's what drives your material selection. Okay, other installation requirements, connections. So the temperature rating associated with the ampacity of a conductor shall not exceed the temperature rating of any other connector termination, conductor, or device. And what that means is often you'll have a off-the-shelf part, like an off-the-shelf disconnect that you might get from Lowe's or Home Depot. And that disconnect may not be designed for being installed on a rooftop. And so it might have a lower temperature connection that is sufficient for for most of for most of its uses. But then again, you may have a conductor that goes all the way up to the rooftop that has a higher temperature rating than the temperature rating of the disconnect. So it's common to have a disconnect switch with a 75C, a 75 centigrade terminal. And now in a renewable energy system that's exposed to the direct sunlight, your cables have a higher temperature rating of 90C. And so what do you do your calculations at? Do you do them at 90C because you're using 90C cable? And you can use conductors with temperatures with higher ratings for ampacity adjustment and correction of the cable. But you also have to make sure that even though you're doing this ampacity adjustment and correction, that the temperature at the terminal is still not exceeding 75C, or its rated temperature. But that's usually what that means is on your balance of system material, on your conduit, on your spec sheets, you're going to see the temperature labels listed and rated for that. And you can find in the solar specialty equipment boxes that have 90C terminals, and they usually cost a little bit more, but that might gain you a smaller wire gauge that because of not needing to do the temperature derating calculations for the 75-degree terminal. And that's going to come later. That's going to come in section 300. So we'll probably get to that after the break a little bit later today. You might be asking yourself at this point, well, where do I go and get design temperatures? How hot does it get up on a rooftop? How hot are my modules and my equipment up there going to get? And actually, we can, for your design work, you're supposed to use the ASHRAE database, but that ASHRAE database won't convert from the ambient temperature to that rooftop surface. If you want to get an idea of what the module temperature is, we can go back into PV watts, which we've explored in previous classes. So in PV watts, you go and get that monthly weather data, and we see from our PV watts output for every hour of the day, for every month of the year, we get not only the output, the power level of the system, but we will get what the ambient temperature was for that simulated day, and then also what the cell temperature was for that simulated day, so that we can see on this 12-degree centigrade day at noon, the module surface temperature got all the way up to 24C. So I'm not particularly good on my centigrade to Fahrenheit conversions. But let's just go 12C to Fahrenheit. Yeah, so on a 53-degree day outside, the module surface got up to 75 degrees. So, that's actually kind of even though it could be jacket weather, cold weather outside, the module surface could be elevated by 20 degrees. So on a hot day, when it's 100 outside, how hot does the module get? Well, let's find out. Here's an example for Phoenix, Arizona. On a 99-degree day outside, it gets all the way up to 160 degrees Fahrenheit on the rooftop, or 71C. And commonly, the wiring that's rated for inside your home only has that 75C rating, or maybe even less. And so, it's very possible for wires on a solar array or on your rooftop to get to a temperature beyond 75C. So if they don't have that 90C rating, they could start burning up on the rooftop. So just because you have a 60 or 75C cable and it might have all the ampacity allowed for your application, if it's going to be subject to direct exposure to sunlight, you can't just oversize the cable to reduce its temperature. You need a cable jacket that is rated for that elevated temperature. And, we apply discount factors to make sure that the cable does not heat up enough. And when you get into higher and higher temperatures, two things happen. One, you're operating at elevated temperatures, but two, you're buying a more robust cable jacket that can contain the heat of the conductor and not start burning up on the rooftop. And so, when you go and you use cables with more robust jackets, you can get away with less derating of your conductor. Derating the conductor means you're increasing the conductor size. When you increase the conductor size, the resistance of the conductor goes down. It's more efficient and it generates less heat. And so in solar design, and when you're transmitting electricity from a generator to its point of use, you're balancing the environmental conditions, you're balancing derating the conductors, but then there's also efficiency, where often you're upsizing the cables anyway in order to make the system a bit more efficient. So we'll run through these calculations as we get into those sections a little bit later on in the program. But right now we're still back in section 110, installation requirements, spaces about electrical equipment. Electrical equipment needs space. In addition to being firmly secured to a building, not just resting on the conduit that comes up from an underground conduit run, but actually securing the box or metal to the building itself. We need to maintain space around our equipment, and that zone extends in front of the panel and above the panel and under the panel into the side of panels. And so just by looking at this room, this is a messy room, and there's also requirements to install your electrical equipment in a neat manner. And so we can see, say, this fiber optic networking equipment to the left of the service panels. That's not a code violation in the sense that it occupies the same working space of the panel. They're both electrical equipment. Where the code violation would be is that's not installed in a neat manner. And then there's other code violations too. That duct work above the service panel needs to be of a certain height. All of that can be found within National Electric Code, and including spacing from your plumbing. And you see here that hot water heater is likely too close to that fiber optic equipment. Actually, though, fiber optic equipment is dealt in its own section of code, section 800, down at the far end. It has more leniency than other sections because fiber optics is a extremely low voltage system. So, fiber optic systems often will operate around 2 volts, whereas, with tiny little cables. Solar arrays, wind turbines operate at battery chargers, lithium ion battery banks operate at 3, 4, 500 volts, even all the way up to 590 volts under normal operating conditions. They're high voltage, they're dangerous. Generally, if you're a commercial electrician, you have a more rigorous oversight by the state, and you're dealing with higher voltage systems, 480 volts instead of 240 volts. Solar arrays can go even higher than that, but not always are they being installed by electricians on the job site. And so the depth of the working space, how far back does the equipment need to go? That has special rules for what is behind the panel as well as what is in front of the panel. The maximum space is around 4 feet, and the minimum space is around 3 feet. And so if you just keep in the back of your head, well, in the depth from the face of the panel, you need to have around 3.5 feet of working space. And if the room is feeling particularly tight to you, rather than the panels being back to back, or depending on what is on the back of that panel, you may need an additional 1/2 foot. The width of the working space, 30 inches, or the width of the equipment minimum. And that can actually be on either side of the equipment. So you at least need to have the width of the equipment clear at minimum. And then you need, beyond the width of the equipment, a minimum of, from one side to the right or the far side to the left, 30 inches of working space. Now, whether or not that working space is centered or offset doesn't really matter so much. And then the height of the working space. So it's 6.5 feet, or the height of the equipment. So obviously, if the equipment is 8 foot tall, it needs 8 foot clearance. But if it's only 3 foot tall, like this electric service panel, the working space is 6.5 feet. And so the question is, well, is that air conditioning duct a code violation or not? You walk through the door, you see the service panel, you see other code violations, and you might look at that air conditioning duct and say, I wonder if that's a code violation too. And for that electric service panel, it might be that air conditioning duct is in fact 6.5 feet tall. And so from the floor up to 6.5 feet is 6.5 feet of clearance. And where these requirements get tricky is especially when you're involving battery banks. Because if you're doing, say, an off-grid residential home, you're likely working with lithium-ion battery banks, and these things are huge. I have such a home of one of my project sites, and this is how the architect sketched up the room inside the garage. And that's going to be an air-conditioned space where we're putting our inverter equipment and our battery bank. And while there's a sink and a fridge and a desk in here, The client said, we're not really, we can remove the doors and the windows. This is going to be for the inverter room. You can use whatever space you need, but we would like to locate it on the walls. Well, here's our batteries. Now, our batteries are, let me see if I can't pull my laser pointer up here. Our batteries is right here. So our batteries are 38 inches deep, 9 inches wide, and 2 feet tall, and they weigh 1,000 pounds each. So these are hefty, large batteries, and we have 8 of them on the job site. Here's a picture of 10 batteries. I think these are gel batteries rather than flooded lead acid. But what we can just see is off-grid homes, the battery banks, if you're using flooded lead acid type, which generally you are because it's the, cheapest and has a lot of market ability. And as of now, it's still kind of hard to purchase lithium-ion batteries in the US. So the question is, do you have space in your room for these batteries? And also just the practical element of how are you going to get the batteries to the room if you're using heavyweight batteries? Those are issues we talk about more in the battery management class, on why you might choose a 2-volt battery to have 48 batteries in your battery bank instead of a 12-volt battery and have 8 batteries in your battery bank. It's all about, can you move the batteries around, or do you have to carry them in? If you have to carry them in, you might go with the smaller, more lightweight battery and have dozens of them. Well, back on point, this is our inverter system, and we have 2 inverters, and we have electric service panel, and then the 4 objects on the right are the charge controllers. And so in total, our kind of inverter control system wall is 8 feet wide and only 9 inches deep. And so in our case, the 6.5 feet clearance is no problem. There's nothing else going to be along the walls of the building. But going back to our room, if we need 8 feet for our inverter system and our batteries, if we have 8 of them and they're about a foot wide each, in total, our battery bank plus our equipment is 15 feet wide. And then we need 30 inches on a side of each. And so we and then we need 30 inches in addition to that. So what we really need for a code compliant room for the minimum space requirements of this electrical equipment is really a 16 or 17, actually an 18 foot wide room. And we don't have that. Well, I guess we could use that along the back wall. And so this essentially says, well, where are we going to locate our inverters and our batteries if we just want to use a single wall? Can we put them here, or can we put them here? Well, we don't have enough space along this wall to put them here. We'll have to use this wall instead and, get rid of that desk and put the batteries along this wall because that's the only wall that has enough space. Alternately, we could catty corner them and get rid of this doorway and put them on a corner here and a corner there. And say, well, can you stack them on top of each other? Is it possible to, let me get my pointer back. Can we instead kind of, instead of catty cornering them, can we stack them on top of each other? Well, then that we have to consider all 3 dimensions, height, width, and depth. And there's another part of code right after this that says above or below any electrical equipment, other equipment shall not extend more than 6 inches out. And so you can't have one piece of equipment that sticks far out from the wall and another piece of equipment that's kind of inset into the wall stacked on top of each other. Those technically would be different zones it would violate, you would need two different working spaces. So to put them on top of each other, you'd have to have a 6.5-foot section and then another 6.5-foot section, although that would be very impractical for the most part. And so what we have is, the reason why this would be a violation, going back to our spec sheet, is this equipment only sticks out 9 inches from the wall, and these batteries stick out 38 inches from the wall. And so if a client says, I want to use this wall, and you might think, okay, on these charge controllers, they're just kind of, there's not much going on in those charge controllers. There's 4 of them. There's no disconnects. It's just 2 wire terminals each. There's not much going to fail with the charge controllers. The client's never going to need to access those charge controllers. And so I'm just going to put them above the batteries rather than to the side. That would be a code violation as well. And so we look in these rooms, and the question is which of these rooms is compliant or not. These both would be considered damp locations. There's actually a few points about this array that are not compliant. The first is the depth. The batteries stick out more than 6 inches from the service panel. Now, we do have 6.5 feet of just electrical space, and we do have the width of the equipment, or 30 inches of access on this side, aside from that depth violation. But then we also have some other items of concern. The first is the deteriorating agents of these batteries could expose this metal conduit. And you can see this installer didn't care, because they're capping their batteries and ventilating the gas out of the building. But you can imagine a local inspector might say, well, that's not good enough. What I want this to be is in, electrician's gray conduit. Well, then the solar guy might say, oh, but it's a DC circuit. And DC circuits have to be enclosed in metal, and that's why we did an EMT conduit. And the inspector might come back and say, well, that may be the case, but metal conduit still can't be in a battery room. So, what you need is a metal conduit with a PVC coating around it, like that flexible metal conduit. Depending on how tough your inspection is. What we can see is here, it looks like they're going into a PVC bend at this point. So that is a code violation from clearance, and your batteries also need to be accessible for servicing. And so if this end of the battery bank needs to be serviced, and they have a watering system, and so they may only need to access this end of the battery bank, but accessibility of both ends of the battery bank may also be a concern. All right, so let's get into some definitions. Ampacity is the maximum current that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Voltage is the greatest potential between two conductors of the circuit. And so we think about that boulder sitting on the very top of the mountain at a high potential energy. And if it crashed all the way down the mountaintop, if a group of mischievous Boy Scouts pushed the boulder off the mountain and it careened down through the forest and do a lot of damage before coming to a stop at the bottom of the mountain at no potential energy. Well, voltage is not potential energy. It's not the stored energy of the boulder versus the boulder at rest at the bottom of the mountain. The conversion of kinetic energy or potential energy into kinetic energy. The voltage is not potential energy, but it is a potential. It's a difference in voltage that makes the difference. It's the voltage of your high voltage line versus a zero voltage line that causes those electrons to be pushed from high voltage into low voltage, just like that boulder would be rolling from energy from its high potential energy to its low potential energy. Electrons flow from a high voltage potential to a low voltage potential. And so then we have voltage to ground. And it says for grounded circuits, the voltage between the conductors and the grounded circuit conductor. For ungrounded circuits, the greatest voltage between the given conductor and any other conductor of the circuit. Okay, well there's a lot of word salad in that. What does that mean? Well, what that says is you have a grounded circuit conductor, which we haven't defined yet, and then you have ungrounded circuits as well, and they're going to have a difference in voltage potential, and the greatest difference in voltage potential would be considered the maximum voltage to ground. And then you also have nominal voltage, and nominal voltage is the kind of at some point, what voltage level we operate our equipment at and design our equipment for is a function of how we convert electricity from a low voltage to a higher voltage, and down to the brass tacks of how many times do we wind a piece of copper around our electric generator in order to step up that voltage. And so just kind of by tradition, we manufacture transformers at 120, 240, or 480, 277, or 600 voltage, 600 volts. And the actual voltage inside that circuit can vary based on what type of transformer it is under normal operating conditions. A great case in point would be a battery bank that is rated for 48 volts. Then you have a 48 volt battery bank, but you might, for certain batteries like flooded lead acid batteries, have a maintenance feature where you drive the battery bank voltage up beyond 48 volts into the 50 or 55 volt range. The battery may be designed to take 60 volts, but its normal operating voltage is 48 volts, and that would be the nominal voltage. But generally, you don't design around the nominal voltage. Generally, you are designing around the maximum circuit voltage. And then, you also have to consider your operating conditions as well. And that might mean that, sure, a solar array is going to be operating at 30 volts on its spec sheet, and that would be considered the nominal voltage. But its maximum voltage may be something different. Its maximum voltage may be a function of temperature. And so we have to apply temperature correction of factors before we get into our design to make sure those conductors don't burn up. Some other terms: branch circuits. Branch circuits are those AC electric circuits in your home. Solar circuits are not referred to as branch circuits. They're DC instead of AC. And so your solar circuits, instead of being referred to as branch circuits, they're often referred to as strings. It's just industry jargon. But they're also referred to as code as something completely different. So you could have an AC branch circuit on a microinverter array that would be a solar inverter output circuit. Or you would have a DC string running between your array into the inverter on the side of the building, and that would still be, it'd be a DC string. It would also be a different circuit category, the photovoltaic array output circuit. Get into that tomorrow. Continuous loads: a load where the maximum current is expected to continue for 3 hours or more. So what does that mean? Well, we have electrical appliances in our home that work all day, and then we have electrical appliances that we only use for 20 minutes at most a day, like your microwave. And so that gets into a difference between continuous and non-continuous loads. So the question is, well, what would a solar array be? What would a wind turbine be? Would it be, do we size it as a continuous load or a non-continuous load? What about a backup generator that's only going to hang out on the back of your house and not do anything unless you lose power? And a power outage may only last an hour. So is that a continuous load or a non-continuous load? Generally, you have to think about the intended use of the device. You know, that backup generator, even though you might only be using it an hour every 5 years, you know, it's intended for full-time use. A solar array turns on in the middle of the day and it turns off at night, but in the middle of the day it's operating for more than 3 hours. And so a solar array is considered a continuous load rather than a non-continuous load.